So today a little bit more about chapter 3, or actually trying to reach the rest of the chapter 3. How we can handle simple dynamical model and get what we are seeking here. It's just the state equation, as we call them. The only necessary first order set of first order differential equation we need to describe any system. So far we have been taught about sources, effort sources, flow sources. These should now be well known. We have learned about ideal machines, transformers, gyrators. We have learned about resistances. We have learned about inertances and compliances. And now we have also heard some rumors about the junctions, zeros and 1. So this is what we know so far. This is sort of our tools. Quick repeat of junctions. And now I will join some of our domains together, energy domains. So take the mechanicals, both translatoric and rotational, sort of the same logic in those two, and also fluid and electric. They will sort of have the same philosophy when you are setting up junctions, zeros or ones. For mechanics, let us start with one junction. When should you use a one junction? And it comes to mechanics. Well, when you have an object, a part, a plate, a bolt, something that has his own unique velocity, then he has a one junction. Say any part with its own unique velocity. And velocity now either back and forth or rotational velocity. For fluid and electric, we use one junctions when we have the same flow straight through any element. Flow through any element. And an element here can be a resistance, inertance, compliance, transformers, gyrators, whatever. Zero. How should we think in terms of zero junctions when it comes to mechanics? You use a zero junction when you have the same force on each side. Same force on each side of the element. While fluid and electric, they will have a common effort in a physical junction. So that was the theory. If you want now to have a little more concrete examples, say we draw some small figures belonging to this one. Any part with its own unique velocity. That could be a solid plate here, like this. He is actually moving with a velocity, and this plate is hooked up with, say, a force acting on it, a spring here, a damper, something like that. Then this part, this plate, he has his own velocity, and we have a lot of power bonds connecting to it. That's okay. But definitely this part, he needs to be represented with a one junction. No colors again? Ain't that too bad? Okay. I use white. You should use a different color. When you have the graphical figure, you just write a one junction on top of it here. One junction. Should be a one junction here. Here, the same force on each side of an element. So if you have a force acting here, and then you have an element, could be a spring, and then you have the same force, of course you have, acting on the other side. Then here you will now insert a zero junction. So again, use a different color for a zero junction here. For fluid and electrical system, you have the same flow through any element. So here you have a pipeline, and here we have a fluid flow, and then we insert some resistance, so say a narrow piece of the pipe or a small orifice or something. And of course, the entire flow goes through this resistance point here. So same flow, okay. Then we insert a one junction at this point. Or if you have an electric wire, some battery or something, and then you insert here a resistance, like this. Okay. It's the same current going through this resistance, no matter what else happens to the system. Insert here a one junction for this resistance. Physical junctions. Okay, you have a pipeline coming here, and then this pipeline, he branches like this. So one flow comes here, but then Q2 and Q3 goes out with some numbers, we don't know how. But this junction here, that's a physical junction. You will have the same pressure regardless if you're looking in pipe 1 and pipe 2 and pipe 3. It's the same pressure at this point. So the same pressure, that's the common effort. So here you will insert a zero junction. Or an electrical circuit, you will typically have then some junctions, and again here a zero junction. You will have the common voltage at this point, regardless any way you are looking. So here the current is moving, I, and then can spread out through any of these branches. We don't know how, but we know the voltage is the same, regardless the path he chooses further. So a little bit more concrete examples for these four possibilities. I believe we have some nice figures here somewhere with junctions. Let's see. That was junctions here, 3, 3. Here we are, zero junction type. So you see, well, we can have a look at it actually. Start with the top. That's a mechanical problem. Force acting on the spring, acting on the damper, acting on the mass. So how to describe that one? Force hitting a spring, hitting a damper, hitting a mass that can move like that. Draw the bond graph for that one. Okay. Here we have mechanically several elements in a series. So for this, take this spring for instance, you have one force on one end. Of course you find the same force on the other side. So to insert him, you will here use a 0. So now, as you see, I should have had different colors. Sadly I don't. So use a different color for this 0. And then you will insert a spring, a C element, a compliance there. For this damper, again, same force on each side. You use a 0 and then a resistance. For this point here, he has sort of his own unique velocity. The same has these points actually, but they have no element connected to them, so it will be just a waste of effort to insert a 1 junction here. But this point, he has something attached to him, namely this mass. So here will be represented with a 1 junction and then an inertance. This point, well, he is being attacked by source, but again he has no other parts connected to him, so we don't need a junction for that one. That should be the first raw bond graph for that problem. And now you can simplify. You have 2 zeros next to each other, and that's not needed. We don't get any more information when we have them side by side. Remember, for a 0 junction, what was it? A 0 junction, common effort. That means you have the same effort. The effort on all bonds here, same effort. The flow might be different. So here is a Q1, Q.2, Q.3, but the effort is the same. So that means the F here, we will find back between those two. Same F here. Actually, the same F here as well. So if you're using a force here, you already know what force will be acting on this mass directly. So it's actually a boring problem. Never mind that. So same force here and here. Then these 2 0 junctions can be joined together in one single. So the entire problem should look something like this. 1 0 junction and then C element, R element, and I element, like that. This is a force that is effort. So it's a common, so it's an effort source like that. The force is given. Same goes with the other examples. For the electric, see, all the elements are in parallel, but still you now use the same 0 junction for all these elements to describe that system. So here you have a voltage, no, sorry, It's not a voltage, it's the ampere. The current is given. And then we have, let's see, capacitor. You will have resistance. And finally, a coil. Like that. Draw the bond graph. How should you do? How should you do that? How do you think? Where do you start? Well, for fluid and current electric problems, for the natural junctions, you use the zeros. And here actually we have 4 of them. So here we insert zeros, like that. That's where you start. For these elements, you will have the same current flowing through them. Hence, each of these 3 will be inserted through one junction. So here, one junction, and a one junction. So now, well, and also this source, if you like, a one junction here as well, because it's the same flow, the same current goes straight through this point. So also a one junction here. So the raw bond graph for this problem is actually quite messy. So it should look something like this. Let's see. We have a current source. What's the current? That is the flow. So it's the flow source hitting a one junction. Then we go up here, hitting a zero junction. Then we continue, find another zero junction, go down here. Here I meet a one junction connected with a mass, an inertance, electric inertance, a coil. Down here I meet another one junction and I find a resistance hooked on that one, and here a capacitor, one junction and a C, like that. And then we close everything down to 0, 0, and finally back again to the one junction. That is the raw bond graph for that problem. It looks rather messy actually. What is nice with electrical systems, also with fluid systems, we can define sort of a ground level. With electric, we just say anywhere in this scheme you have ground. So typically we do that here at the bottom. So this is ground, or earth if you like, where the voltage is by definition 0. For fluid systems you do it in the same way, but then with the pressure, saying that you have an outlet out to the atmosphere, and we always calculate with gauge pressure, not the absolute pressure. So we sort of subtract the atmospheric pressure, meaning atmospheric pressure equals 0 pressure. So if this one is ground, meaning zero voltage, then what is the power through these bonds here? Well, remember the power bond here. Now you have the effort, and for electric systems that was the voltage U, the flow Q dot, well, that's the current. The power you find by multiplying these two together. If one of them is 0, the power is 0. Hence, all bonds connected to ground will have 0 power. But then we don't need them, do we? Can be removed, removed. Take them away. They don't do anything, no additional information from them. 0 power, remove them. Okay, then we have these bonds pointing to nothing. Remove, remove. Then these 1 junctions here, they have only 2 bonds. Any junction with only 2 bonds, well, then it's not a junction anymore. Then you can remove him. Remove this one, and this one, and this one. Then it should be a little bit better. Here we have 2 zeros next to each other. Join them. So we are removing that one. Let's see, for this 1 junction, now also only 2 bonds. Remove him. What are we left with? You have an flow source hitting 0, and from this 0 you will now have one C, one R, and one I element. So you will have the same image as this one. Any questions to that one? Okay. For the 1 junction, sort of the same logic, but then flipped, you might say. For the mechanics, here you have a mass. This is now an object which has its own unique velocity. So there, definitely, clearly, we are going to need a 1 junction to describe this mass. And then we have hooked up a spring and a damper, and here a solid wall, like that. Yeah. Draw the bond graph. Okay, you have a force hitting something with its own velocity. That's 1 junction. And clearly, then when this 1 junction has mass attached to it, you insert the mass directly. Then he branches into 2 separate elements here, a spring and a damper. And here the philosophy was the same force on each side, insert them with 0 junctions. So here, 0, 0, and here we have a spring. Down here we had a resistance. And then finally they join together here at another point where you have the same unique velocity. That's a 1 junction. But this is a solid wall. He doesn't move. So the velocity x dot is 0. Sort of the same as this ground level here. When the wall or this point doesn't move, he's attacked with a lot of forces. That's nice. But when the velocity is 0, the total power entering, exiting this wall is 0, so we can remove him. So no power in this bond or in this bond, since the velocity is 0. Then for these 2 zeros here, both of them has only 2 bonds. They can be removed. And we are left with what? You have a source hitting a 1 junction, and then inertance, compliance, resistance. So there you have a 1 junction type. Effort source, since here they say it's the force acting, then obviously. For the electric and also for the fluid, use 1 junctions when you have the same flow going straight through the elements. Here they will be in a series, So you will have a 1 and up to an R, 1 up to a C, and 1 up to the inertance, and so on.
No.
Any questions? You will be better by handling these when it comes to you need some more training, more exercise. Exercise 3 is going to be a pure mechanical problem. Exercise 4, that is actually an important exercise. There you will be given a whole bunch of different small cute little problems from all the different energy domains: fluid, electric, mechanical, and then you have to do the entire bond graph for all of them. Yeah, should we look at that one as an example? Maybe we can. See if we can find him. Non-linear, where is he? Ah, he's a little boring. Let's go back to one of the first examples I showed you. This one. So the job here, find the equation of motions that describe this problem. We have given the pump, we know the pressure just initially here, just after the pump. This one is given. Find the motion. So here we have some fluid string, cylinder here with a piston and area. Force then acting on the mass with a spring, and we have some sliding resistance, and so on and so forth. Now, for from last time when we looked at that problem, we found the solution by looking at the physical laws. Now we should find the same solution, meaning finding the differential equation describing this, by using bond graphs. So let's try. Example, this is called an actuator. How you position the mass to a certain desired behavior. So we start, we have a pump here with a long flow, and inside here we actually have a resistance. Our fluid, yeah, I have it here, yeah, and then large cylinder, a piston, and then the mass here, M, hitting a spring, and then a solid wall. And here we have sliding resistance. What do we call it? RB. And here we have a spring. Mass is an inertance, like that. Here we have the pressure and the area. And finally, the pressure as a source. Pressure source as a function of time. Well-known function of time. positive direction to the left, x dot. Okay, draw the bond graph for that one. It's a mixed problem. We have a little fluid, we have a little mechanical. So you should always use the generic symbols. Not use pressure, mass, spring stiffness, K, things like that. Use the generic bond graph symbols, inertance, compliance, resistance, and so on. You can always label them 1, 2, 3, or F and then B or whatever, but use the generic names. Okay, here we have a source hitting something that has its own velocity. We have resistance, but the flow goes straight through it, hence it will be a one junction. For this resistance RF. Everything has to go through the pipe here. And then we continue like that. What kind of source is it? Well, we know the pressure. The pressure is given. And in fluid, the pressure, that is the effort. So this is an effort source. Now, we know the pressure inside this cylinder. And this pressure acting on an area produces a force. So there you will have a coupling, pressure, a force. They are clearly coupled directly. And what type of element can do this type of coupling? Yes, a transformer. Effort is coupled with effort. If you're in doubt, then check the other one as well. If you know, say, you know the velocity here for the mass, you know how fast he is moving, then you know the velocity of this area here, and then velocity times area, that gives you then the volume flow. So the volume flow directly coupled to the velocity. So here, effort coupled with effort, flow coupled with flow. Yes, it is a transformer, not a gyrator. Then we are here. Here we have something which moves with its unique velocity in the mechanical world. Yes, it's a one junction. He has mass connected to him, so we can insert that one directly. Down here, we have a resistance, and further down we have a solid wall. Resistances, they should be inserted with a zero junction, so you can think a small zero in this layer between the wall and the mass, okay? Small zero here. So I do it like this, small zero out to the RB, and continuing down to the solid wall, which is an one junction with x dot equal to 0. But we know this is going to be removed anyway, so you don't have to draw it. A little bit of experience, you want to draw these. But for a complete raw bond graph, yes, they belong. So for now, actually, I have it here. It's very small, but it's here. One junction where x dot equal to 0. Continuing, I find a spring. So insert a spring, okay? Same force on each side, hence a zero junction. And then we insert the compliance, the C, continuing, and then again a solid wall. So one junction because he has its own unique velocity, but this velocity is 0. There you have the raw bond graph. Everybody agree with me on that one? Okay, then it must be right. Now let's see how we can simplify. One junction with the zero velocity can be removed. Then this zero junction has only two bonds, can be removed. Also this one junction, zero velocity, no power on that bond, hence this zero junction has only two bonds, can be removed. And now I have two one junctions, but I have a transformer in between them, so I can't really do anything. I just have to leave it. So here, we simplify the bond graph. RF hitting transformer, hitting one junction where we have mass, we have a spring, and we have another resistance RB. There we have it. Okay, now we have the bond graph. Let's try, if we can, to what's called to annotate this bond graph. Annotate, identify all efforts and flows. Identify all efforts and flows on all the bonds. On all bonds. So here is actually where we need a little bit thinking. We need to use the head a little bit. Now I am using a little bit mix of symbols. So never mind that. We could have called them here effort 1, effort 2, effort 3, and then made a list beneath it with then effort 1 equals, effort 2 equals. Some people like that. I actually like to use the bond graph directly, which then implies that you have to use a very big piece of paper. You need a big figure because you're going to have a lot of algebra on each of these different bonds when the problem is complex. This one is not so bad, so let's see how it looks. So here we can start with the pressure source. This one we know. This one is given. Well-known function. So here is something that we know everything about. Then we can also say, since this is an effort source, we don't care about the flow. That's not interesting. So we can skip that from the problem. He will never enter into any equations. We can always find out what he is later on, but what the flow is here is not interesting. Needless to say, he hits a one junction anyway, so the flow will be given here from these two bonds. Yeah, well, we can set up this flow. Volume flow Q going here. Then actually we have one equation already. If we know the volume flow here to be Q, what is the pressure drop on the other side? Well, assuming this was a linear problem, laminar, then we have a linear connection between the pressure and the flow. So the pressure here, P, what did I call it? P1 equals the volume flow multiplied with RF, like that. What do I get here? That should be a pressure. Now we have one equation around these junctions, a zero junction and a one junction, namely the summation rule. The flow is constant, so same flow on all these bonds, but the effort has to add up to zero. So the first equation that we get now will be what comes into this one junction, PS, equals what comes out. So that should now be P pressure 1, and then we call him pressure number 2 plus pressure number 2. Okay, if we know pressure 1 and we know the source, we can calculate the pressure P2. No problem there. If you know the pressure P2, well, that's actually the pressure here inside this cylinder, we can find what is then the force on the other side. There we have a connection through the transformer. Pressure times area gives force. So then we know this force. So that is nice. That is nice. For the mechanical problem here, a common velocity for this lump of mass, yes, that's true, but we have 4 bonds with possible different forces acting on it. Fair enough that we have the same velocity, but how is the force distributed among them? Well, we really don't know, do we? But we have to set up the equations for each and every one of them, for these 3 here. So say you have a force 1 here, he will then equals mass times acceleration, Newton's second law of motion. And what do we have on the other side for one junction? Well, it will be something like an x dot, then equal the time integral of him, v, divided by the inertance. So that would be one way around it. We'll come back to how to handle these later on. So for now, yes, we know there's a coupling between flow and effort when we have an I element. Same goes with a C element. If you know the flow, then you know the force here should then be equal to the what is it? The flow, the position actually, divided by C. And finally, the force number 3 here will be given by this RB multiplied with the velocity x dot. Here also you will have a summation rule. The sum of all the forces has to end up with 0 when the flow is the same on all bonds. So yes, you will have the force entering equals F1 plus F2 plus F3. So there you have the 2 summation equations. You will have a whole bunch of more equations. For this transformer, you will have 2. Pressure 2 equals transformer times force, and the velocity x dot equals transformer multiplied with the volume flow. You will have more equations. Here we have 3. How many do we have? 3. You will have 1 equation for each of these elements, RF, RB, I, and C. So RF, I, C, RB. That's 4 more. So in total, 8 equations. 4 here and 1, 2, 3, 4 here. 8 algebraic equations. Not all are algebraic. Some of them will be differential equations. So yes, this is possible to find the set of equations. Possible, but much work. So we don't like to do it, and we are not going to. Any questions? Then we'll see how we can avoid all this work in the next lecture. We take a break.